Welcome back, everybody. I want to start today by talking about some abstractions for machine learning, or some meta comments about how we think about machine learning. So, as an analogy, when you write a large computer program, generally you divide it into different subroutines and modules. And those of you who've done a lot of large software know that it's important to have strong abstraction barriers between the different modules in your program, because if you don't, the program will become increasingly unwieldy and hard to debug and hard to maintain. So these abstraction barriers you insert in your computer programs, well, when you're thinking about machine learning, there are some very clear-cut abstraction boundaries in machine learning as an intellectual topic too, which will probably be matched by boundaries in your code, or should be, when you write machine learning code. And very roughly speaking, we can subdivide a lot of machine learning algorithms into 4 different pieces. And it's useful to think of it that way because sometimes you can swap out one piece and replace it with a different piece. So I want to give you 4 levels of abstraction when you think about machine learning. And the top level will be the application that you are ultimately working on and the data that you are given to work with that application. Now, part of this level abstraction is just answering basic questions like, for instance, is the data labeled? Or to put it another way, does it have classes or other values associated with it, or not? And if the data are labeled, then generally we're solving some sort of supervised learning problem. And then you can ask, are the labels categorical, meaning dividing the world into different classes? Or are they more numerical, quantitative? In which case we're usually doing a regression. On the other hand, if your data is not labeled, we're probably doing some sort of unsupervised learning. And you have to ask yourself what you want to do with that data. For instance, are you mostly interested in the similarities and dissimilarities between different parts of the data, in which case you might use a clustering algorithm? Or maybe you're more interested in the relative position of different bits of data compared to other bits of data, in which case you might want to do dimensionality reduction. Now, there's a lot more I could say about the application, but most of the things that you can say about the application are specific to specific applications. So every application, you're going to have different goals you're trying to achieve, different things that you know about your data. You may have advanced knowledge about that subject matter that allows you to do things like design good features or otherwise set what the model should be for your data. And that's going to be the second level of abstraction, is what is the model? Model's a pretty general word. I would think of the model as answering the question, what types of hypotheses are permitted? In other words, what things, like what ways of dividing classes or what ways of computing a regression value are we allowed to use? And so, for example, if you are using a machine learning algorithm that uses a decision function or a regression function, then you have to decide, are you going to stick to linear decision functions or linear regression? Or are you going to do polynomials? Or are you going to do something completely different, like in a few weeks we'll learn about logistic regression, which uses a logistic function, which is a natural choice for probabilities. Or maybe you have the kind of problem that justifies going all out with a neural network. And there are some models that don't use decision functions, and for some problems, those might be better. For instance, if you are using the nearest neighbor algorithm as a classifier, then that gives you a completely different model than a decision function does. I mean, there is an implied decision function because once you finish training your classifier, whenever you input a point, you're going to get a class out. So that's the decision function. But a nearest neighbor classifier does not explicitly compute a decision function like a linear classifier does. It's more of an after effect of doing nearest neighbors. And another algorithm that matches that description is decision trees, which we'll be learning about shortly before spring break. Another thing you need to think about in your model is what are the right features? If you're doing image analysis, then maybe edge detectors are the right features to use as input to your classifier or regression. And a lot of effort goes into deciding what are the right features for different applications. And this requires very specifically understanding your application. And all of this feeds into the question of, do you want a low or a high capacity classifier or regression algorithm? And what capacity means roughly here is just how sinuous can the decision boundaries be, or just how curvy can the regression function be. If you have high capacity, then you can make more complicated distinctions, but you need to have good enough data to support those distinctions. So, like linear classifiers are usually on the lower capacity end of things. Neural networks are usually on the high capacity end of things. And the reason why these decisions are important is, first of all, they're going to strongly affect whether you are overfitting your data, whether you're underfitting your data, or whether you're fitting your data just right. Another important aspect of machine learning is that sometimes we want to use it to do inference. What is inference? Well, we want to actually not just build a model that a computer can use to classify, but we actually want to have a model that's comprehensible, like a human can look at it and say, oh, the reason why this flower is being classified in this genus is because it has this many leaves. And so often we want to use data to do scientific inference. And that implies you need a model that's simple enough to understand. So that's not usually a neural net. Maybe that's a decision tree. So models are kind of the metaphysics of machine learning. Before you even start to learn something, you have to restrict the class of models that you're going to allow yourself to learn. And how you do that is a bit of a black art. But once you've chosen a model, then the next step, often, not always, but for many of machine learning algorithms, is that now we try to boil down the model into some sort of optimization problem that chooses the best model to fit our data. So you've got certain model parameters, and given that you've got certain data, what is the best fit of those model parameters to that data? And here's where we get down to actually defining what are the variables, what are the parameters in our model, what is the objective function that we are trying to optimize, and what are the constraints that we have to obey while we're optimizing. And so there are many different possibilities here. We could do sort of basic unconstrained optimization, which is what the perceptron risk function, or what the perceptron algorithm does, is it just takes the perceptron risk function and tries to minimize that without any constraints. Or you might use much more complicated constrained optimization algorithms like linear programs, quadratic programs, or convex programs, which is what a support vector machine does. If you're doing regression, you might use least squares linear regression. It's one of the most popular algorithms in the world. Or you might do something different, like logistic regression, polynomial regression. Another thing you might do is use principal components analysis as a way of optimizing certain objective functions. There's many possibilities here. But defining an optimization problem is kind of something you do formally, rigorously, mathematically. You write it down. Once you've written it down, now you have to write code that solves that optimization problem. Maybe approximates a solution if it's too expensive to find an exact solution. And so the bottom of our 4 levels are the optimization algorithms. And of course, the one you hear about the most in machine learning in general is the gradient descent algorithm, because it applies to so many different objective functions, and because stochastic gradient descent in particular is just a natural fit to an objective function that is a sum of something simple over many, many data points. But there are other algorithms that you should know about. You should at least have heard about the simplex algorithm for linear programming. You should know that the singular value decomposition is one of the best ways to do principal components analysis, and we will discuss that late in the semester. So the point here is that we have 4 different levels of abstraction for how you can think about your machine learning application. And it's pretty important when you're working on these codes or solving problems or writing down the math to know which level of abstraction you are working on. And if you if you don't know whether you're working on what is your model, what is your statistical model going to be, or whether you're working on the optimization algorithm that tries to find the parameters for that model, if you haven't got that sorted out as 2 different things in your brain, you're going to get very confused. So always try to be conscious, and I'll try to help you be conscious of where we are in this diagram. I want to be clear that in this course, we're mainly focusing on the middle 2 levels. We're going to talk a lot about models, and we're going to talk a lot about the optimization problems that those models bring up. We will talk a little bit about optimization algorithms, mainly gradient descent and SVD, but almost always what you're going to do is you're going to find a software library for that particular optimization problem that's been written by somebody else and is far more fast and robust than what you could do in a short amount of time. And you're going to use that because optimization algorithms, fortunately, tend to follow into a bunch of well-established classes for which there's very good software available. A little bit more about the second level, the model. This is going to have a huge effect on the success of your learning algorithm. The assumptions that you made before you ever started learning anything make a huge difference. And you sometimes get a big improvement in your results by tailoring the model to the features to fit the structure of your specific data. So choosing the model really depends on understanding your application and your data. The model also has a big effect on whether you underfit or overfit, as I said. And if you want to do inference, you have to choose a model that has a simple structure, like a decision tree. And lastly, when you're picking a model, you have to pick a model that gives you an optimization problem that can be solved. If your model gives you an optimization problem that's NP hard, you might be better off moving to a less accurate model that can be solved in polynomial time. Some optimization problems are just too hard. When you change one of the levels in this diagram, you usually wind up having to change all the levels underneath it as well. If you change your model, you're probably switching to a different optimization problem, which means you need a different optimization algorithm. And I do want to say that not all machine learning algorithms really fit this four-level decomposition well. Like, for instance, nearest neighbor algorithms, sometimes you don't really use an optimization algorithm at all. Sometimes you do. We'll get to that at the end of the semester. But for most of the things we're going to learn this semester, we do have these bottom two levels, the optimization problem and algorithm for solving it. Any questions about any of this so far? Yeah. Why is SVD an optimization algorithm? The singular value decomposition does optimize something. It is, for instance, if you want to find a low-rank matrix that is in some sense a good approximation to a high-rank matrix, the singular value decomposition gives you all the tools you need to solve that problem exactly. So we'll talk a little bit more about that late in the semester. Other questions? So I want to spend most of the rest of the lectures familiarizing you with the different kinds of optimization problems that you're likely to encounter. And the names of a few of the optimization algorithms used to solve them. When you're designing new models, an important skill is to be able to spot what model fits what optimization algorithm, and to know what optimization algorithms people know how to solve and have good software for. Also to know what optimization problems are NP hard and you aren't likely to find good software for them. And that's what knowing about this helps you go from an application to a well-defined optimization problem. So just recognizing optimization problems is important. So the simplest optimization problems are the unconstrained ones where somebody gives you an objective function, which we will call f, and we want to find the point in weight space that minimizes that objective function, or maybe maximizes it sometimes. People set up their objective functions to be maximized rather than minimized. Usually we hope that the objective function we want to optimize is continuous. It always will be this semester, more or less, though that's not always the case. But someone gives you a continuous function f, and we want to find the minimum point. One thing that's nice, a nice property to have in f, is smoothness. So f is said to be smooth if its first derivative, its gradient, is also continuous. But we can't always take smoothness for granted. I've already given you an example. Remember the perceptron risk function? It's not smooth. That makes it a little bit harder to optimize than a smooth function, though you can still do it with stochastic gradient descent. So I want to talk about minimizers of functions. So first of all, most of you have probably heard this term before. When you have a function f, a global minimum of f is a value call it w, such that the value of the function at w is less than or equal to the function anywhere else, or anywhere else in the valid domain of that function. But often when we want a global minimum, we can't always have one. Sometimes we have to settle for a local minimum. A local minimum of f is a value w such that fw is less than or equal to fv, not for every v in the domain, but just for every v in a sufficiently tiny ball centered at w. So in other words, you cannot walk immediately downhill from w. This makes a little more sense if we draw a picture. So here's a graph. The horizontal axis is w, and here's a function. So I'll assume that outside of that range, this function only goes up. And then, knowing that, we can identify several local minima such as this point here is a local minimum because you can't roll downhill from that point. If you look at a tiny region around that point, you go a little bit to the left or a little bit to the right, f doesn't get smaller. And likewise, this point here is a local minimum. Technically, it's just the value of w that's a local minimum. So formally speaking, I should really say this point and this point are the local minima. But you get the idea. This is also a local minimum, though that one is special because it's also the global minimum. And in this case, it's the only global minimum, though you can have more than one global minimum if the function is flat over a certain region at the bottom of the trench. And so one of the most basic, important things to understand about optimization is that for many of the optimization problems that we will care about, finding a local minimum is kind of easy. The intuition is you just roll downhill until you get to the bottom. But for general problems on general objective functions, finding the global minimum can be really hard or impossible. And so we generally try to avoid models that require us to search for a global minimum. We want a model where the local minima will be good enough. It should be said, though, that there's a happy exception to the general rule that finding global minima is hard, and that's convex functions. So this is not quite a mathematically rigorous definition, but this is a geometric, intuitive definition. We say that a function is convex if, well, let's look at any 2 points on the graph of the function, say x and fx, and y and fy, and connect them with a line. And if that line does not go below the function, then we say the function is convex. So, example of a convex function. Here's some axes. The convex function. So, the idea being here is if I pick this point x and this point y, and then we map up to the point on the graph, this is x comma f of x, and this is y comma f of y, and we draw a line connecting those two, a straight line, you'll see that the red curve nowhere goes above the blue line. And that's true for any pair of points that we choose on that graph. So that's a convex function. Note that flat spots are okay. This is another example of a convex function. So we have seen an example, of course, the perceptron risk function is convex. And that really helps us to optimize it. That's why the perceptron algorithm is guaranteed to work on linearly separable points. It's also non-smooth, which makes it a little harder to deal with. Smoothness often helps us develop good optimization algorithms. The way that we know that the perceptron risk function is convex is the fact that it is a sum of very simple convex functions. So remember that the perceptron risk function is a sum of loss functions, and each of those loss functions is essentially piecewise linear with two parts, a flat part and a part that goes uphill. So it's pretty easy to see that that graph is convex and that this graph is convex. You have to imagine that in higher dimensions, of course. This is just with a one-dimensional feature space, these graphs. But in general, the risk function, even in high dimensions, is very simple with two linear pieces, and it's convex. And it's a general rule, you can prove, that the sum of convex functions is always a convex function. So add up a bunch of these simple convex risk functions, and simple convex loss functions, and you get a not so simple convex risk function. All right, so let's suppose we have a convex function. I'm assuming it's continuous. I won't write down continuous, but assumed continuous and convex. And to be strictly correct, we also have to assume that this function is defined over a closed convex domain, but I'll let that slip by for now. The important idea is that when you have a function that you know is convex, and you want to find the minimum or the minima, there's basically three possibilities. The first possibility is that it might not have one because it might go to minus infinity. And the obvious example of that is when you just have a straight line as your function. Well, if you walk downhill, you're going to keep walking downhill forever. So that's always a possibility, even for convex functions. But if that's not the case, the other two possibilities are that it has just one local minimum, which also is the global minimum, or it could have more than one local minimum, but if it does, all those local minima will be like touching each other, meaning it's a connected set of local minima. And all of those local minima are global minima. Because all of them have the same objective value. All right, and of these three, the last one is the correct description of the perceptron risk function, because remember that the perceptron risk function, generally if your points are linearly separable, there will be a pi slice in weight space. Within that pi slice, the risk is 0. Everywhere outside that pi slice, the risk is positive. So that's, think of that pi slice when you think of a connected set of local minima. That pi slice, or that set of local minima, will also always be convex. Now, in two of these cases, you can just walk downhill until you find a minimum. So in essence, some version of gradient descent should work in these two cases. Though, of course, if there is no minimum, then gradient descent will just keep going down and down and down forever and never reach the bottom. We're going to see examples in other convex objective functions, like when we do logistic regression. But there are a lot of applications where you don't have a convex objective function. Like neural networks are famous for that. Neural networks try to optimize an objective function with lots of local minima, and they usually don't find a global minimum. But in that case, we have to settle for a local minimum, and sometimes that's good enough. Question? Well, an example, if you come back to this graph right here, so in this example here, the minima are all of the points at the bottom of the trough, going off to infinity. So here's an example where you have an entire ray in your domains, in your weight space, where all those points are global minima and local minima. And so that can happen with a convex function. Does that answer your question, or is there more? Yeah, continuity is very important for this. Yeah. Continuous and convex. Mm-hmm. Mm. Why is finding a global minimum so hard? The main issues are, one, that there could be so many local minima, and you don't necessarily know where to look. Like, here's a lot of local minima, and, well, what I'm going to try to do is I'm going to hide the true global minimum in a really narrow region. So, you don't know that the function looks like this until you probe it. If you don't actually think to probe in this little region here, you're not going to find necessarily that there is a bigger or deeper minimum that you missed. And then the second problem that makes this even worse is that usually we're not doing this in a one-dimensional space. We're doing this in a multi-dimensional space, and that means there's literally an exponential number of places you have to look to find that trough. Yeah. How can we tell if a local minimum is good enough for us? Validation. How well does your classifier work on your validation set? You know what scores you want, and at the end of the day, that's what matters. That all of this is details by comparison. Other questions? Mm-hmm. Is there a good way to decide where to start gradient descent? In general, no. That's actually a pretty hard problem and one that gets kind of overlooked. So You know, with neural networks, what they usually just do is pick a completely random point in space as your starting point, which seems crazy, but I haven't really heard anyone say that they've got a better way. Other questions? But it is a great question, and one that probably deserves more research, I have to say. Where do you start? Why don't we know more about starting points? I don't know. I just want mostly now to familiarize you with some names and terminology. Unfortunately, we don't have time to go into much depth in these ideas, though we will explore gradient descent a little bit more. Gradient descent is, in machine learning, by far the most popular algorithm for optimizing smooth objective functions. And strangely, the most commonly used version is what I'll call blind gradient descent, which essentially means we use a learning rate, like the perceptron algorithm does. It is blind because it's not actually looking to see how far do I need to go downhill. It just takes a step. It has a hardwired parameter, alpha, step size, epsilon, and it takes a step, which, well, by old school optimization point of view, this seems like a kind of dumb thing to do. The smart thing to do would be to use line search. I'm leaving a space in the middle. And in the middle, there's stochastic gradient descent, which is also usually done blindly. So what is a line search? Well, I'll say more about that in a second, but what it does is instead of just blindly using some parameter epsilon as your step size, it actually looks ahead. Once it's chosen the direction it's going to search in, it walks along that direction and tries to find a minimum point along that one-dimensional curve. Seems to make sense, right? So it's actually pretty interesting that that's not used very often in modern machine learning. It's one of the something that seems strange from the school of old-time optimization experts. I also want to mention Newton's method. We are going to see this later in the semester when we talk about logistic regression. We'll briefly review Newton's method, which sometimes can be very effective for logistic regression. The main pitfall of Newton's method is that you have to compute the Hessian matrix of your function, and that's only really computationally sensible if you have a small dimensional space, if you have a small number of features. So you know, if you're classifying objects with 10 features, this is fine. You can build a little 10 by 10 Hessian matrix, no problem. If you are using a neural net with 1,000,000 parameters, you're not going to build a 1,000,000 by 1,000,000 Hessian matrix. So Newton's method just isn't used for neural networks because there's too many parameters and the Hessian matrix is too big. Another interesting algorithm that overcomes this problem because it does not need the Hessian matrix is called the nonlinear conjugate gradient method. Which, by the way, includes a line search as one of its subroutines. I also want to mention that when you have a non-smooth f, you can still do gradient descent, as we do in the perceptron algorithm. But certain other standard algorithms don't work because they require second-order information. They assume your function is smooth. So Newton's method doesn't work now. Line search methods that depend on second-order information don't work anymore. But there is a separate branch of research on non-smooth optimization that has had some pretty nice successes. The most famous algorithm that you'll hear of specifically for non-smooth functions that's used sometimes in machine learning is called the Broyden-Fletcher-Goldfarb-Shano algorithm, named after its inventors, or BFGS for short. And so I'm not going to say anything more about that except to just alert you to the fact that it exists. It has to be said, though, that none of these algorithms try to find the global minimum unless the function is convex. So they're just looking to walk downhill until they hit a local minimum, and then they're happy. I just want to come back to the concept of line search. The idea of line search is that you're going to divide gradient descent into two pieces. The first piece is you pick a direction where you're going to go downhill, which is usually minus the gradient. And once you've chosen your search direction, then you do a more sophisticated one-dimensional search called a line search. You're walking along a line, and you're trying to find a local minimum along that line. And because you're reducing the problem to one dimension instead of d dimensions, when you're solving an optimization problem in one-dimensional space, you can get a lot more sophisticated with your methods. You know, it's much easier to do second-order methods because you don't need to do tricks. You're just working in one dimension, or even higher-order terms if you want. So you can do some much fancier things with a line search than you can in general spaces. And so the idea here is, again, you alternate between deciding a direction to go in high-dimensional space and doing a one-dimensional optimization problem along that line, back and forth, back and forth. And line search methods include the secant method, though that method is predicated on the belief that you have a smooth objective function. Or you can even use the second derivatives, in which case you're using probably the Newton-Raphson method. And this really only works for things that are smooth because they have to have well-defined second derivatives, preferably ones that don't vary too fast. But if you have a function, if you're optimizing a non-smooth function, then your line search needs to be non-smooth too. And there are line search methods called direct line search, of which the most famous is the golden section search. So again, I'm not going to go into any detail about most of these things this semester. I'm giving you these terminology in case you want to do further search or exploration on your own to solve machine learning problems or optimization problems that come up. Neural networks are very interesting in how they fit into this space. Neural networks are an unconstrained optimization problem. Sometimes it's a smooth objective function, sometimes it's not. It depends on how you structure your neurons. They almost always have many, many local minima, not just one, not all of which are necessarily globally optimal. And although neural networks sometimes benefit from line searches or even from second-order optimization algorithms, when the input data set is very large, researchers almost always favor the dumb, blind, stochastic versions of gradient descent, which, again, probably came as a big surprise to traditional optimization researchers. But there's something special about objective functions that are a sum of little functions over millions of data points that changes what kind of optimization algorithm works well. Any questions about any of that? Mm-hmm.
In practice, would you just try all these and see which ones perform best in validation?
Would you try all these? You could try a bunch of these and try to use validation to pull them apart, but it would take a lot of work to code all of these up. In practice, usually what you try to do is understand your application and then come down to one or a few choices that you can compare based on knowledge of what optimization algorithms have traditionally worked for which problems. So, and I'm trying to give you a little bit of guidance on that, but there's a lot that you can only learn by, reading the research literature. Yeah. So the question is, if you have an extremely high dimensional parameter space, how does that influence your choice of algorithm? I don't think that it influences it as much as the smoothness of your space, the smoothness of your objective function, or other properties of, well, convexity being the other big property. But when you have a huge number of parameters, the main thing to understand is that you can't form a Hessian matrix. That doesn't necessarily stop you from doing all second-order methods. There are methods that try to use curvature without forming a Hessian matrix, but those are hard to formulate well. Mm-hmm. A direction that's not actually what? Oh. What happens if the direction that you choose to descend in isn't a very good direction? That definitely happens. It happens quite often, actually. What happens then is that your progress is just very slow. This can even happen with gradient descent. You might think, oh, I'm walking in the direction of steepest descent. That should be a good direction. No, sometimes it's a terrible direction. And that's one of the weird things about optimization for machine learning, is that I don't feel like researchers have really tackled that problem as well as they should have. So it is a real problem, and there isn't a good solution to it. Yeah, it happens. Mm-hmm.
Has a version of simulated annealing or any other such algorithm been used to find an approximate global descent?
So the question's about simulated annealing, which is a somewhat famous optimization algorithm, the kind that one of my professors referred to as a cocktail party optimization algorithm, because it's really interesting to talk about, but not always so interesting to use. But what I would say about simulated annealing is, and also genetic algorithms, just to bring in another cocktail party algorithm, is that they are best on very non-smooth functions, like functions that are almost chaotically random. Those are the ones where you want to use simulated annealing or genetic algorithms. For almost everything that comes up in this class, there's sort of more regularity to our objective function f, and so more traditional algorithms will usually work better. Where you want things like simulated annealing is when you're optimization landscape just looks crazy, like there's no, you don't know which direction is downhill because it's so weird. Mm-hmm.
I wonder, are all those algorithms are unconstrained algorithms?
Mm-hmm.
Can we add some constraint to the level of this algorithm?
Yeah, I'm going to spend the rest of this lecture talking about how you add constraints. So let me kick that off. So a lot of optimization problems you'll want to solve. You'll want to apply constraints of some sort. And I will just very briefly talk about the simplest version of constrained optimization, which is when your constraints are equalities, not inequalities, and they're smooth. We're not actually going to see any examples of that this semester, so I will brush over this topic quickly, but I just want you to know that it is a well-studied topic in optimization. And so suppose that your goal is, again, to minimize or maximize some function f of w over some weight space. But now you want to add a constraint or several constraints of the form g of w equals 0. Where g is a smooth function. And I just want to say g might be a vector. So when you see gw equals 0, that's not necessarily just one equation. It might be a whole system of equations. Because if g is a vector, we're setting every component of it to 0. So essentially, we're solving a bunch of scalar equations. Also, I want to point out that this equation, gw equals 0, this actually, you can think of that as defining an isosurface in our weight space. And so we're looking for a point on that isosurface that maximizes f or minimizes f. And this is where the topic of Lagrange multipliers comes up. And they are a pretty interesting way to solve these kinds of problems. And what Lagrange multipliers are essentially is a trick for transforming a constrained smooth optimization problem to an unconstrained smooth optimization problem. Well worth noting, but doesn't come up in this class, so I'm going to move on to constrained problems that instead of having equality constraints have inequalities. Question? Does f what? Well, the technique of Lagrange multipliers does generally assume that both f and g are smooth, yes. And may not work if they're not. So what actually is a better fit for most of the problems we actually want to solve in machine learning is not equalities, equality constraints, but inequality constraints, which we've already seen multiple times with support vector machines and the perceptron algorithm. And so for that, we want to solve various kinds of convex programs. I'm going to start with linear programs and then work up to quadratic programs. But just knowing what a linear program is a pretty important basic start, something that you want to learn to recognize. So a linear program is an optimization problem where I give you a linear objective function. I want to maximize or minimize. And then I have a bunch of linear constraints. And these are well, we can have equality constraints, but the ones that make this interesting are the inequality constraints. Now, for reasons of tradition, it's much more common to specify a linear program as a maximization problem rather than a minimization problem. But it doesn't really matter. You can do it both ways. And so what we are maximizing is some linear function c dot w. I don't need to add a bias term or a constant to the end because that's not going to change what the maximum is. But we're maximizing c dot w subject to a bunch of constraints. And we can write those constraints as a single inequality, AW less than or equal to B, as long as you interpret that correctly. The interpretation is that this is actually a system of inequalities, not just one inequality. A is a matrix. Specifically, it's an n by d matrix. B is a vector with n components. And A and B together express a system of n linear constraints. And so the way to think about this notation here, where I've written AW less than or equal to B, well, the left-hand side's a vector, the right-hand side's a vector. You're supposed to apply the less than or equal to component-wise. And so if we pull out one component, then that is the constraint that if you take row I of the matrix A and take its inner product with the weight vector, that has to be less than or equal to the ith component of vector B. So this makes a lot more sense, though, if we actually draw the constraints. So let me draw some linear constraints. All right, so what I'm drawing here is we have a two-dimensional weight space. And in that weight space, we have a bunch of linear inequalities. And each of those linear inequalities defines essentially a line in two-dimensional space that you're allowed to be on one side of that line, you're not allowed to be on the other side of that line. And when we take all of those lines together, the place you're allowed to be is inside here. So here in green, what I've got is the set of all of the points that obey all n of these linear constraints. And the set of points is pretty important. We call it the feasible region. Oh, by the way, this is in W space, just to be clear. This is weight space, the space of this vector W. So W is the variable. The A's and the B's are fixed. They're given to you as inputs. And so now I can pick any point I want in this feasible region here. But I don't want just any point. I want to optimize this function, c dot w. I want to maximize that. So what is c? Well, think of c as being a vector pointing in some direction. And so when I want to maximize c dot w, what I'm saying is pick the point in the feasible region that is furthest in that direction c. Which point is that? Well, in this example, that would be the point right here. You know, c is pointing. That point is more extreme in that direction than any other point in the feasible region. So that is going to be our optimum. that point. And that's what we want to find. That is what linear programming software will find for you. Only it'll do it in more than 2 dimensions. It'll do it in high dimensional spaces, usually pretty efficiently. All right, so let me set down some of these definitions. The set of points W that satisfy all of the constraints, that's the green region, is, well, we call it a polytope. And that polytope is always convex. I'll tell you what that means in a second. And so that polytope is called the feasible region of our linear program. I'll call it F. And then our optimum is the point in that region F that maximizes C dot X, or in other words, is furthest in the direction C. All right, so this naturally brings up the question, what does convex mean? The definition of convex polytope is not quite the same as the definition of convex function, but they're related. By the way, this also brings up the question, what does polytope mean? Let me do convex first. A point set, call it P, but I'm thinking of F, is said to be convex if, for every pair of points in that point set, the line segment that connects P to Q lies entirely in that point set. So, for example, here's a point P in the feasible region. Here's a point Q in the feasible region. If I draw the straight line connecting them, the line segment connecting them, the whole line segment is inside the feasible region. Since that's true for every P and Q in the green region, the feasible region is convex. My other question was, what is a polytope? A polytope is just a high-dimensional generalization of a polyhedron. So think of a polyhedron, but polyhedron often just means in 3 dimensions. This is in any dimensional space. You just generalize the idea of a polyhedron to higher dimensions. Now, generally, you're going to find that the optimum fits some of the constraints with equality. But not most of them. Well, usually not most of them. Depends how many there are, of course. But usually most of the constraints at the optimum point, the inequality will be strict, but at some of the points, the inequality will be equals. And the ones that are equals are special. They're called the active constraints of the optimum. All right, so coming back to our figure, what are the active constraints? Well, there's two of them. There's this line here, because this line passes through the optimum, and the other line that passes through the optimum is that one. Now, in a support vector machine, the active constraints correspond to the training points that touch or violate the slab. So in other words, this active constraint here, it comes from some training point. And this active constraint here, it comes from some other training point. And in this example, those are the two training points that are defining where the slab is. And thereby, they're the ones that are picking out our decision boundary of our SVM. And by the way, those training points that correspond to these active constraints, those are called the support vectors. There was a little bit of discussion of those, I think, in homework 1. Oh, another thing I wanted to point out is that sometimes in linear programs, sometimes there's more than one optimal point. And to give an example of that, suppose that instead of C pointing that way, imagine if C was perfectly vertical like this, then all of these points on this edge of the feasible region, they would all be optima. They would all have the same value of C dot W. And so you would have an entire facet of the feasible region that's made up of all optima, all equally good solutions for that linear program. Always, they will form a convex region, a convex facet of the feasible region. So just be aware that there's not always a unique optimum. You could have infinitely many optima. So part of the significance of linear programs is that simply by defining the feasible region, you have defined the set of all linear classifiers that separate the linearly separable points. So every feasible point gives you a linear classifier that correctly separates all the points, 100% training accuracy. So you could even write that as a linear program as follows. Let's find the weight vector W and the bias term alpha that maximizes. All right, I'm going to do something weird here. I'm going to set C to 0. So I'm just going to say maximizes 0. I know that sounds crazy. Doesn't everything maximize 0? Well, that's the idea. We want everything in the feasible region to count. And so if I write this and add the usual SVM constraints, that is an example of a linear program. Again, a bit of a weird linear program because the objective function is 0, but this is a perfectly valid way to write a linear program whose solutions are all good linear classifiers that correctly classify this data. And you might ask, well, what if the points are not linearly separable? Then what? Well, then the feasible region is empty. And this is kind of an important thing to understand. The data are linearly separable if and only if the feasible region is not the empty set. Now, this applies to the maximum margin classifier. Although the maximum margin classifier is not a linear program, it's a quadratic program, and I'll explain the difference in a minute. But the feasible region is exactly the same concept for both cases, whether it's a linear program or a quadratic program with linear constraints. The feasible region is exactly the same thing. And so everything I just said is true for the maximum margin classifier. When you set up your quadratic program, if you find out that your feasible region is empty, then the points are not linearly separable. And I will talk about quadratic programs in a second, but before I do, I just want to, again, list some names of algorithms for solving linear programs that you can look up if you're curious or if you want to dig deeper. And we have to, of course, start with the very famous simplex algorithm of George Dantzig. Which was invented way back in 1947 and is indisputably one of the most important algorithms of the 20th century. Huge amounts of computer time are spent solving linear programs by the simplex algorithm. Roughly speaking, what simplex does is it takes your feasible region polytope and it walks from vertex to vertex of that polytope, always in a gradient descent fashion, always choosing an edge of the polytope that will take it to a better objective function until it finds the optimum. But I should mention that there's a competing set of methods called interior point methods that sometimes have their own advantages, especially when you go to things that are more complicated than linear programs. So a big picture thing I want to point out is that linear programming algorithms have a very different feel than continuous smooth optimization algorithms. And if you ever study them, you'll see that they feel much more combinatorial in nature, more discrete, less smooth and continuous math comes into it, more combinatorial choices come into it. And in that sense, they almost feel more like graph algorithms than they feel like continuous optimization algorithms. If you knew which constraints were going to be the active constraints at the optimum in advance, then it would just be a numerical problem. But figuring out which constraints are going to be the active constraints is the hard part. There's an exponential number of different choices, and it's not easy to devise an algorithm that might not take exponential time in the worst case. And so, again, I feel like simplex and other linear programming algorithms have a very computer science feel because the discrete part is more important than the continuous part, whereas unconstrained optimization problems like stochastic gradient descent tend to have more of a continuous numerical mathematics feeling to them. I will mention that linear programs pop up everywhere in engineering and science. They're hidden everywhere, and so they're usually in disguise, though, so it's very helpful to develop the skill of learning to recognize a linear program when one is presented to you. And lastly, again, a linear program solver can find you a linear classifier that separates linearly separable points, but it can't find you the maximum margin classifier. And so we're going to need something more powerful, quadratic programs. Before I go on to those, any questions? Mm-hmm. What if the feasible region is unbounded? That happens often. You could very easily have a feasible region that goes to infinity in some direction. And, well, if the direction you want to optimize in is not one of those directions, then you're in luck. You can still find an optimal point. Most linear program solvers work just fine with unbounded feasible regions. But if your c vector does not point up, if it points down, then in this example there is no optimum. You can get your objective function to be as big as you want it, so there's always a better point. For our context, where we're looking for linear classifiers that correctly classify all the training points, as long as there is one point in class C and one point that's not in class C, this will never happen. You'll never get an unbounded, well, you'll never get a linear program where the solution can go to, like the cost can go to infinity. Yeah.
Will there ever be a bounded feasible region, but a non-convex polytope?
Because we are using linear constraints, you can't have a non-convex polytope. If you wanted to use nonlinear constraints, things change a lot, but then the problems get a lot harder, so we usually don't do that in machine learning. So lastly, a quadratic program is very similar to a linear program, except now we have a quadratic objective function. And we're going to require that that objective function be convex. In other words, the Hessian matrix of the quadratic function we're optimizing has to be, well, generally positive definite, though sometimes positive semi-definite will do. But we still have linear inequality constraints. We're not going to let those go quadratic. So our goal is to find some point W in weight space that minimizes a function of the form f of W is W transpose times some matrix Q plus C transpose W, subject to the same constraints as in a linear program. So again, the constraints don't change, just the objective function now has a quadratic term in it. And I generally expect Q to be positive, definite, and symmetric. And I think most of you know this from previous classes and from the homework, but what it means for a matrix to be positive definite is that the first term, W transpose QW, is always greater than 0 for every W that isn't 0 itself. And the nice thing about having that positive definite Hessian of our objective function is that the quadratic program always has only one local minimum, which is therefore the global minimum. Though a natural question to ask is, what if you have an optimization problem like this where Q is not positive definite? Well, if Q is indefinite, then your function f is not convex, the minimum is not always unique, and interestingly, quadratic programming can be NP hard in that circumstance. So don't expect to solve problems where Q is indefinite. If Q is positive semi-definite, then f is convex. Most quadratic program solvers will work, but there may be infinitely many solutions. And of course, our big quadratic program that we've already learned about is finding the maximum margin classifier. And I want to just show you an image that gives us a sense of what it means to do quadratic programming. So